Welcome back to GFE0007, Data Analytics Made Easy for Beginners. And today we are going to dive into one of the most critical topics in data science. And if you can really master this topic, then you'll be ahead of most beginners in the field. So we are talking about overfitting and how to avoid them. So this is the roadmap for today, and we'll begin by defining what is the core concept of overfitting and what does it mean. And then we look at how it happens in real world practice. And the most importantly, we are going to discuss what are the strategies to avoid it. Now let us start with the core concept. As we may have explained in the previous lecture, first is we need to clarify the goal of the data science and modeling. So when it comes to modeling, we're not just trying to explain the past or describe what has already happened. The true objective of when we do the modeling is for us to be able to predict the future or to estimate the values that we do not know yet. So you might build a model that can explain your historical data perfectly, but it could be that the model will fail when you try to predict based on whatever parameter that you have developed and you try to apply it using the new data sets. So this is why the data analytic thinking would require a focus on generalizations, or the ability of a model to work on a new data set, or the ability of the model to work in the real world and not just based on the limited data that you use as the training sample before. So let's talk about this 100% accuracy myth. So imagine a consultant comes to your office and says that they have a model that is 100% accurate at predicting which customers will leave your business. So your initial reaction might be to be impressed, but if you are a true data scientist, then you can become immediately skeptical. Because if a pattern looks too perfect, then it usually means that the model may have simply memorized the random noise in the data rather than learning the actual underlying signal or the patterns inherently in the data sets. So we can see this in its most extreme form, which we call as the table of model paradox. So imagine the model that is just a giant lookup table where every single training instance is stored. So if you asked about a customer that it has seen before, then it can be 100% accurate. But the moment a new customer arrives who is not in the original table, then the model will fail completely. And this would prove that the memorization is the most extreme form of overfitting. So let's officially define generalization. And what does it mean? So generalizations is the property that allows a model to apply effectively to the data that it has never seen before. So we want models that can capture the general trends in the population, like for example, older customers tend to stay longer. And this prediction of staying longer is based on the attribute of the customers, which depends on the age. So we must try our best to avoid models that capture sample idiosyncrasies, which are just memorizations of individuals that were already in the training data sets before. So now we distinguish between the sample and the population. So every data set you work with is just a small, limited, and finite sample, and this sample can come from a much larger and sometimes infinite population. So within that sample, you may have two things. Number one is the signal, which is a true underlying patterns that you want to capture. And the second one is the noise, which is just a random chance of occurrences, the differences between the individuals that may not really help to explain the predictive powers. So when this overfitting happens, the overfitting may happen the moment your model mistake that random noise for the true signal. So there is a famous quote by Ronald Coase: if you torture the data long enough, it will confess. So in a large enough data sets, you can find a correlation for almost anything if you look hard enough. But often the most, this is just a spurious correlation, which is just a connection that may look real in your sample, but they don't actually exist in real world. So we can visualize this using a fitting graph. So this graph plots the model performance against model complexity. So the horizontal x-axis represents the complexity. For example, how many variables or how many nodes in your model. So from the left, you may have like a very simplified model. As you add in more variables and more nodes in your model, then the model complexity is going to increase. And the vertical y-axis represents the error rate or the accuracy. So to find the truth, we track two different curves, one for the training data set, which is blue, and the other one is the holdout set, which is also called the test error. So as you can see, the training error will reduce as you increase the model complexity, and this is when overfitting happens, because as much as you increase the model complexity, the model become really fit to the training data, and so the training error will reduce. However, as you increase the model complexity to the training data, the holdout set or the test error will increase after a certain point, and this is when we say that this is the problem of overfitting. So the best fit is somewhere in the middle, something that minimize both the training error and also the holdout error. Now we look at the training curve. As you make a model more complex, the error on the training sets, which is the data that it is learning from, always goes down. And a flexible model can always find a way to fit the point it already has seen. And because of this, the training accuracy is a very deceptive measure of success. Now let's look at the holdout set or the test set curve. So initially, as the model learns real patterns, the error on the holdout set decreases, but eventually the curve reaches a minimum point and it starts to go back up. And the upward turn in this area is the visual signature of overfitting. It means that the model is getting smarter at the training data, but it may be dumber at the real world. So our goal is to find the sweet spot, which is in the middle here. And this is the exact point where the holdout error is at the lowest. At the same time, the training error is also going down. So let's look at how overfitting happens in practice, and let's look at the tree induction. So for example, in the case of decision tree, we can grow the tree by splitting the data into smaller and smaller group. For example, starting from the root node, and then we split them into the following node, and then we further split them until we grow a very large tree. And if we don't stop the growth of the tree will continue to grow until every leaf is pure, meaning that it only contains one type of results. And oftentimes, these leaves may end up representing just a single data point, which is you're trying to predict individual person by looking at all the attributes that is associated with this individual. So these massive trees are highly prone to overfitting because they are too specific. Okay. And we can also see this in mathematical functions. In linear model, for example, complexity increases as you add more variables and attributes. So you may have like x1, x2, x3, x4, and you can add more. Adding the non-linear terms, for example, like x squared, will give a model more leeway to bend around data points. and it's not just limited to linear relationship. And geometrically, you can fit a line to 2 points or plane or 3, and if you have enough dimensions, then you can fit a very complex hyperplane to any data sets, no matter how messy it will be. So let us consider the impact of outliers. What is outliers? The outliers is the data points that are just further away from what we considered as the normal when we look at the distributions of the data. So everyone else is clustered around the mean, but the outliers might be a very, very large number or very, very small number. It's a highly atypical observations. So a very complex model might try to warp its decision boundary just to catch this one single outlier. So what happened is you may correctly classify one weird point today at the cost of misclassifying thousands of normal points in the future. And then let's look at the spurious correlation. So let's say you use the last digit of a person's phone number to predict if they will leave your service. Let's say by chance, in a small group, maybe people with the number 7, they're more likely to churn. Okay, so an overfit model will actually create a rule saying that if their phone ends with 7, then they will churn. And of course, this rule has zero predictive value for the general population. This is just one example, but sometimes it really happens. And this is why overfitting can be bad for businesses, because it provides a false sense of security. It can lead the companies to waste money by targeting the wrong people. And in fact, the complex and overfits model often perform worse than the simple base rate models that just predict the average. Now, what are the strategies to avoid this from happening? So our most essential tool will be the testing datasets or the holdout method. What we do when we have the data is we split the data into two parts. The first part is the training set, where we train the model to learn from this training set. And then we have another set which we call as the testing data sets or the holdout sets, which is hidden during the training. So this data will not be involved when it comes to building the model. So we can think of the test sets as the lab test to see if the model actually works. And the golden rule is never ever test on the training data sets. Instead, we build the model using the training data sets, but we test the performance using the testing data sets. And we address a common problem. What if your holdout set was just lucky? And to solve this, we can use the technique where we call this as cross-validation. We can split the data into k folds. Usually we use between 5 to 10. For example, like if you have 100 observations, then you divide them into 10 groups. So each of the group will have like 10 observations. And then we split this data into 10 groups. And then we iterate k times. K means like 10 times. And each time you use k minus 1, which means that 10 minus 1 fold for training. And the remaining 1 fold is used for the testing. And then you repeat it again. So for example, in the first iteration, you use the first 9 group, and group number 10 is used as the testing data sets, and then you iterate it so that the second time you build the model using a group number 1 until 10, but you leave out group number 9, and then group number 9 become the testing data sets. And at the end of the day, you just get the average of the model performance for all the 10 iterations. Now, don't confuse fitting a graph with a learning curve. Okay. But first, we look at the cross validation, its stability, and the variance. So this cross validation can help us to measure stability. It gives us the multiple score in which we can calculate the mean and the average performance and the standard deviation, which may show us how the performance varies from one sample to another. So if the variance is high, it can be a red flag that the model might be unstable and it would likely overfitting. Now let's talk about the fitting graph, which shows the performance versus the complexities. And then the learning curve shows the performance versus the amount of training data. And here's some strategic insight. So if your learning curve is flat, buying more data won't help. So you need a better model or probably a better features, which means that probably the features or the attributes of the data might not be adequate, so probably you can add in more features in your data set. Now let's talk about the complexity control, especially for trees, which is called the pruning. Pruning means you cut down a certain branch of the trees. So the pre-pruning means you stop splitting the node if it has too few instances. For example, if the leaf is already reaching like 30 observations, then we stop growing the tree because we do not want to have a tree that tries to fit exactly to one person. Yeah, we want to have a more general patterns. And the post pruning means that first you grow the full, very large and massive decision tree, and then what you do after that is you cut down some branches that don't actually help improve the accuracy on the testing data sets. Another strategy is by using the attribute selections, where you should only use the most informative attributes. So for this one, you can use the forward selection methods, where you start with the 0 variables and then you add them one by one, or you can use the backward elimination, where you start with everything and you remove the least helpful variables. And fewer variables mean fewer chance for the model to get distracted by the noise. But of course, we want to maintain a certain level of variables, so it can still capture the main underlying patterns. Now let's talk about the concept of regularization. So traditionally, the objective is to maximize the fit to the training data, but a regularized objective might be different because the objective of regularization is to fit the data minus some penalty for complexity. So you put some value of the penalty if the data becomes complex. Or in other words, we penalize the model for having too many variables or weights that are too large, and this will force the model to become smoother and more robust. And then the problem of multiple comparisons. Let's say if you test 1000 random stock, one will look like a winner just by chance. And similarly, if we try to have 1000 model variations, one will look kind of good on the test set just by luck, and this is called as overfitting the test set. If this thing happen, then the solution is to keep a final validation set that you only use once, at the very end of the project. So instead of dividing the data into two parts, which is the training data sets and the testing data sets, now you divide them into three parts, where you use the training part to build the model, the testing part to test the model performance, but you have another data set which is only used when you are already happy with the performance of the model using the testing data set, and it is used at the end of the analysis to ensure that overfitting on the testing data sets doesn't happen. So as a manager, this might be some tactical advice. You should always ask, how was this model validated? So if this group of data scientists only show you the training accuracy, you can reject the proposal. If they don't mention about the holdout sets or the cross-validation, be extremely cautious. Always look for that sweet spot analysis in their work. And don't try to put so much trust in the predictive accuracy, especially a very high predictive accuracy on the training data sets, because when you try to apply the model to a new data set, you may not be the model might not perform as you expect it to be. Now let's summarize and let's look at some of the key takeaways. So number one is training accuracy is a lie because it only measures memorization and not really prediction. And simple is often better. We can only add complexity if it helps generalization, because what we want from a model is the important patterns that we want to capture from the model, but we do not want to capture the noise, which is the individual differences. And complexity control is mandatory, and to control for complexity we can use pruning, we can use selections or regularization, and always use a cross-validation at the end of the project, which is the gold standard for professionals' evaluations. Now that we have reached the end of the slides, if you have any questions, just post it on Spectrum. Thank you.